So this lesson here is about the basic derivative rules. So we're going to learn more or less all of the shortcuts for finding a derivative. So I'm going to start right off. We're going to go through about 7 or 8 of these. So this is the first basic one here. And this is telling us that when we find the derivative of a constant, we get 0. And the natural way to think about this is to think about a constant function, right? So you can think of something like this, where y is equal to c. So you could think y is equal to any constant function. And notice when you look at the slope of this line, y prime is equal to 0, right? And that's the interpretation here, is when you take the slope of a constant function, you get 0. Okay, so the next basic one here that we'll add to this, we're just going to upgrade a little bit. The derivative of the x function is equal to 1. And in a very similar way, you can think of the function y equals x. So we'll just do that pretty quickly here. So this again is a very familiar function in mathematics. So when y is equal to x, notice that the slope of that line is 1. Right? So the derivative here is equal to 1. So this is the operator notation for the derivative, and we read this as the derivative of x equals 1, and here if y is equal to x, y prime is equal to 1. Okay, so the next one here that would be pretty natural, this basically comes for free, is that anything of this form, right, if you take the derivative of a line, so anything of the form mx plus b, the slope of the line is equal to m. Right? So we just look at this here, and the slope is given by the coefficient of x. And so when you think about the slope of the tangent line, right, it makes sense to say that when you differentiate this, you get m out of it. Okay, so those are 3 really quick ones. We're going to go through some more general ones now. So the first really big one here would be this one. And this one is so important we've got a name for it. So we call this the power rule. And I think the name makes sense because it works with power functions. So when we find the derivative of x to the n, there's a certain procedure to go about doing it. The power goes out in front, we leave the x alone, and then we drop the power by 1. So a simple example of this is to think of a power here. So I'm going to take something like x to the power of 2. So when you find the derivative of this function, according to this rule, the power goes out in front, you leave the x, and then you drop this power by 1. So you can indicate it this way. So 2 minus 1, right, is just going to give you 1. So the connection to make here is the transformation, right? When you have the function x squared and you want the slope of the tangent line, it becomes this function here, right? Y equals 2x. So it should be noted that the mathematics books are pretty fussy about this and talking about what kind of number n is. So they usually start out with n being rational, etc. So this power rule, though, as you get deeper and deeper into calculus, you find that this rule is strong enough that it works for any real number. So n can be any number, and this rule will apply. So I think something important to remember to look back on is that finding the derivative of something like this is very time-consuming. So if we quickly look at the older way of doing this, right, this is just to remind you that the power rule is a good thing, because we can see how this is really a shortcut to this method. So when you think of the squaring function, this was the older way of doing things, right? To use the derivative definition, the x plus h definition, and letting h go to 0. And so we use the squaring function twice here. We multiply all of this out, we cancel out some factors, and then we divide an h out top and bottom. And then you can see at the very end of the work, as h goes to 0, here is f prime, right, the derivative. So this is the long way of verifying it, but the important thing to take from the power rule is this is a nice little shortcut for all of that work. So I want to look at just an example of this, just so you can get a sense of how versatile this rule can really be. So you can think about something like the square root function, right? G of x equals square root of x. And we might not interpret this as a power function, but we can rewrite it this way. X to the power of 1/2. And as soon as we see that n is equal to 1/2. So then we can find the derivative of g. So the power will go out in front, 1/2, and x is there. And then we drop the power by 1. So 1/2, if you subtract 1, will become negative 1/2. So it takes this form here. And then what we can do is to just polish this up. We can write 1 over 2x to the positive 1/2. And then if you wish, you can bring this back to the square root. Right, so we could express it this way. So again, the big connection to make is that there's a transformation of some sort that has occurred. This is the original function, root x, and this is the derivative, right, 1 over 2 root x, and it's all about using the power rule. Alright, so the next one here that comes to bat, this is a nice one. This here is called the constant multiple rule, and the reason for that is we're taking a function and we're multiplying it by a number, and we're going to find that derivative. So this is a pretty simple one to understand, because you can see that if you're taking a function and you're multiplying it by a number, then the derivative doesn't change all that much, right? So the constant shows up in the answer as part of the answer, and then you just differentiate the function. So let's take a look at an example of this. Okay, so something like 6 divided by 7x cubed. So this one's a little bit difficult to recognize, but you'll notice that we know how to differentiate something like x cubed, but the 6 over 7 is standing in the way. So we could say, we could argue that 6 over 7 is really playing the role of c here. So one thing we should do first is perhaps rewrite this as 6 over 7, and then we can write this as x to the power of minus 3. So this is the original function y, and then so we say to ourselves, this is the c here, and then this is the function that we know how to differentiate. So when we take a look at this, y prime, right, according to this rule here, will equal 6 over 7, and then we have to find the derivative of this function. So that would require using the power rule up here. So this would be negative 3, and you write down the x, and you have to drop the power by 1. That's a little bit tricky, right? So we have negative 3x, and then drop negative 3 to negative 4, and then this will be our derivative, and we take these two and multiply them. Okay, so this will give us a negative 18 in the numerator, and the denominator we have a 7, and then we can bring the x factor down here. So it looks like negative 18 divided by 7x to the 4th, right? So again, this is our function y, and this is the transformation here, y prime. Alright, so one of the last ones to show here would be this one here. And this rule here has the name the sum and difference rule. And it's a very simple looking rule. It really says if you have more than one function at play, so for example you could have two functions that you're adding or subtracting, then finding the derivative is no harder than just finding them separately, right? So you find the derivative of f and g by themselves, and then do whatever operation you're asked to do. And this rule is nice because it will extend to more than two functions, right? So you could have 4 or 5. So I'll move this up here. So again, I'll just make something up here. Y equals x cubed minus 7x squared plus 8. So this is a nice little problem because you can think about all of the other rules that we just talked about. So if you want to find the derivative, you can write y prime or dy dx, very different notations. So this one here is saying that you can treat each of these like separate functions, right, and just do them one at a time. So this one is a nice power rule. So we have 3x squared. And so notice the second one will be a power rule and then also the constant multiple rule. So -7 will come directly down, and then x squared becomes 2x to the first power, right? And then these are multiplied. And then this was the very first rule, right? If you differentiate a constant, it vanishes. It becomes 0, and then you can simplify. So we have 3x squared minus 14x. Okay, so this here would be your y prime or dy dx. Okay, so just one more rule to talk about, and then this lesson is more or less done. And this is a very special one that warrants some attention. So we'll spend a little bit of time on this. So if you have forgotten what E stands for in mathematics, this is a very special number that arises in many different places. And it has some qualities that are similar to pi, right? It's an irrational number. It's impossible to represent its decimal entirely, right? And there's no real pattern to what's happening here. And so this is the exponential function, right? It shows exponential growth. And the reason this rule is significant is it's telling you that when you transform or find the derivative of this function, e to the x, the derivative is unchanged, right? So we think of a transformation like x squared, right? When you differentiate it, it becomes 2x. Or if you differentiate 7, it becomes 0. So there's some kind of change here that occurs. So this is one of the, or the only non-trivial function in all of mathematics, where if you find the derivative of the function, you don't see that transformation. Okay, so what we're going to do is just to validate this graphically in a very informal kind of way. So I'm going to put the graph up here. I'm going to plot a couple of points. Okay, so one of the points here, if you think of the function y equals e to the x, right? So if you plug 0 in here, e to the 0 is 1. So one of the key points here would be right there, right? 0, 1. And then another one, if you plug 1 in here, you get e to the first, which is around 2.7. So at 1, we're going to be around 2.7. So I'll do my best to spot that point there. And then this is exponential growth. So the curve has this kind of characteristic to it. And then asymptotic to the x-axis here. So this is really what the graph looks like. And I'm being really rough, just plotting a couple of points. So this point here, we identified as 0, 1. And this point here is 1e. Okay, so one way of really understanding what does this statement say is to actually just think about it in terms of functions. So if you think y equals e to the x, right, and think about what this rule means, it's really saying that y prime is the same, right? It's also e to the x. So now if you connect these two, right, these are the same, so that's really telling us that these two are a perfect match, right? So this function e to the x is special because y prime is equal to y. So this statement here in green is a profound one, right, to think about the connection here. So it's really telling you that the slope of the tangent line is equal to the y value of the function, right? So we can just note that here on this side, this is the slope of the tangent line, and then y here just indicates the function value. So this is a y value. Okay, and it's telling you that they are the same. So now if you go up to the diagram, you can convince yourself at least a little bit that this statement appears to be true. So if you go to this first point here and you sketch a tangent line, so I'm going to put one in right there, okay, and you can ask yourself, what is the slope of the tangent line? It's given by what we have here in the box. So the slope of the tangent line is equal to the y value of the function. So if you look at this point, the y value is right here. It's that second coordinate. So the slope of this line is equal to 1. So m is equal to 1 there. So this condition occurs all throughout the curve y equals e to the x. So if you move to this second point here, you can see the same thing going on. So I'll put a tangent line here, try to illustrate it. And you can visibly see that this tangent line is much steeper. So when you ask yourself here, what is the slope of this line? Again, the slope is given by the y value. So the y value at this point is equal to e. Right? So m here is bigger than 2.5. It's about 2.7. And you can see that kind of trend. So as the curve grows steeper and steeper, the tangent line is matching the y value, right, or the y coordinate of the function.